Last time, we've shown why we need a link budget for the analysis of the eye height. In this video, I will continue to show the image of why we need a link budget in a SerDes system, but focus on the eye width this time. Now, we are very familiar with the performance metrics of the eye height and eye width. Also, we understand not only the signaling will impact the bit array, but also the timing will declare the bit array if we are not sampling the input at the right time. So, we will go through all the timing images one by one from all the impairments here and cross with the eye width margin of the link budget for the timing margin expansion. To make the timing margin easy to communicate between different symbol rates, either the jitter requirement or the eye width would prefer the units in UI unit interval instead of picosecond or nanoseconds, and most standard or documentation. The first eye width budget would be the TX output jitter. As we discussed in the jitter video, the low frequency jitter will not impact the link performance, since the CDR must track the low frequency jitter from the TX, and the timing margin between both input data and recovery sampling clock will still be 0.5 UI if the clock sample in the middle of input I between transitions. Ideally, the eye width seen by the eyes is still 1 UI. On the other hand, if the TX has too much high frequency jitter, then the CDR cannot track, and the phase error would be too much to open the eye width. Therefore, to make the ecosystem of the SerDes work properly between vendors, any product standard defines the TX output total jitter filtered by a high-pass filter must be less than a ballpark 30% UI. Some are slightly larger, and some are slightly smaller than the 30% UI, which might be used as a worst case in the link budget. But if you have a customized circuit block, such as all the TX and X in your design, then the TX jitter budget could be more specific to the RJ and DJ respectively. A quick reminder, the RJ is unbounded, and the corresponding P2P jitter will depend on the bit array. The DJ is bounded, but there are lots of sources from the DDJ, DCD, SI, and PI impairments. Alright, what's the next link budget? Correct. Residual ISI after equalization EQs. The estimation procedure is exactly the same as the why link budget 1 video we discussed last time. Just apply the equations you plan to use and run the EQ simulation over PVT and find the minimum eye width or maximum deterministic jitter for the figure of merit. For the same case study, both CTLE and DFE were applied to equalize the 22 dB loss at the next rate. Therefore, the CTLE can open the eye at about 72% UI eye width, and the DFE would help to open the eye width further to 88% UI eye width at the sample front end. But do you see any subtlety here? Think about the worst case TX output jitter images for 5 seconds. Bingo! The TX output jitter in the simulation does not include the total jitter that the eyes cannot track. Therefore, the link budget of the eye width at the eye sampler input is not accurate, as you can see in the major TX output eye diagram. In addition to the DJ, the little green dot would be the RJ, which could be the high frequency jitter that the RX CDR cannot track, and the phase error would degrade eye width at sampler. To be clear, in the EQ simulation under the ASI, not all the TX impairments are included in the simulation. And furthermore, this TX might not be the only input source of the RX, and so many types of TX from different vendors could be the RX input sources. So, what can we do? Think about the specific images of all the SerDes protocol standards for 5 seconds. Right, that's the beauty of the specification in every protocol, which would limit the TX output total jitter. TJ equals RJ plus DJ at a high frequency must be less than 30% UI. If you don't know which TX will connect to your RX, you could just assume the worst case 30% UI into your link budget without running lots of time-consuming simulation efficiently. Therefore, in our link budget exercise here, we could easily get the residual eye width margin to be 58% UI for both TX and RX residual eye size here. Let's move to the next one. Do you have any idea of what else item we should go through? Think about the noise images for 5 seconds. Right, we just simply go through all the items we had last time, but focus on the jitter this time. The first one will be the high frequency accumulated RJ of the RX front end CTOE all the way to the sampler or CDR input. As we know, in the white noise video, the random noise from the device would be the voltage noise, but the vertical will translate to the voltage uncertainty, to the timing uncertainty at the data transition, which you call it random jitter RJ. Similarly, if there is any deterministic disturbance on the voltage, that voltage uncertainty will also translate to the timing uncertainty, which you call it deterministic jitter DJ. For total jitter RJ plus DJ of frequency content higher than the CDR tracking bandwidth, we should add that jitter into the jitter budget. Therefore, the RJ simulation is needed to capture the RX front end intrinsic RJ in addition to the DJ. To be clear, any signal integrity SI or power integrity PI with substrate package as parameter model is a must, such that we may capture the extra deterministic jitter from the deterministic voltage distances in addition to the previous DJ evaluation from the residual ISI only. Therefore, as the voltage margin, all the DJ should capture the impact of the reflection, crosstalk, and surprise noise precisely. Then, what's the next? Think about the decision maker images for 5 seconds. Bingo! Again, the decision maker is the clock sampler. So we must focus on the timing as the digital flip-flop. From your digital class 101, what are the time requirements of any flops you must follow? Correct. The setup and hold time are the hard rules here, which means the clock arrival time must be later than the data arrival time, and the time difference must be larger than the flop setup time requirement. On the other hand, the clock arrival time must be earlier than the data arrival time, and the time difference must be larger than the flop's hold time requirement. Therefore, the clock sampler has a similar setup and hold time requirement to consume the time margin, which must be evaluated and added in the link for the sampler input residual offset. That's another less significant translate from the DC offset. Despite that, we need to watch out Alright, would that be all from the TX to the CTOE and all the way to the sampler? Of course not. What else? Think about the sampling clock for 5 seconds. Right, again, the decision maker is the clock sampler. So any phase error between the sampling clock and input data will translate to the timing jitter, which reduces the eye width margin as we mentioned. Therefore, we must watch out for the intrinsic RJ from the RX sampling clock itself, especially the high frequency RJ due to the VCO, other sources from the PL, or the clock distribution buffers, since those high frequency jitter cannot be checked by the CDR to reduce the phase error. Is that all or something else? Think about the clock DJ images for 5 seconds. Correct. In addition to the RJ, we need to watch out for the sampling clock's DJ as well, which could come from the CDR's hunting jitter if the band CDR is used, or from the supply noise of modulating the delay of any buffers inside the CDR. To be clear, all kinds of CDR would have different DJ sources depending on the topology you choose, and you must evaluate all the DJ from the sampling clock carefully and put them into your link budget. Okay, everything looks good since we discussed the data path RJ and DJ, and the clock path RJ and DJ. Anything else? Perhaps think about other subtleties, such as half-rate clocking images for 5 seconds. Excellent! For the high-speed C-link of more than 10 gigabits per second, I believe most people would apply half-rate clocking to reduce the power and boost performance. Above 56 gigabits per second, more and more people may even apply quarter-rate clocking. But nothing is free for the multi-phase half-rate or quarter-rate clocking. The phase accuracy is very critical, since it will degrade the eye width because of the clock's phase error. From the simple image of the half-rate phase error delta phi, you can tell the eye width is decreased, or the phase error between the clock and data is increased. To be clear, on the left-hand side, the positive phase clock would hit the right transition quicker than the negative phase clock would hit the right transition by a delta phi. Equivalently, the negative phase clock would hit the left transition quicker than the positive phase clock would hit the left transition by delta phi. Therefore, the 2 delta phi phase error between the positive phase clock and negative phase clock would be the DJ or eye closure in the eye width project. Again, the eye width could have further degradation due to the other subtleties in your system, and feel free to leave any comments below about your system, such that we could have a further discussion to help you. Here is the summarized image of why we need a link budget for the analysis of the eye width in SerDes. All the evaluation items are very similar to the eye height we discussed last time, but we are using the clock sampler or clock comparator. Therefore, we need to evaluate the sampling clock path as well. To summarize what we need to put in the eye width margin in the table, let's apply our case study here. First, the TX total output high pass filter jitter RJ plus DJ from the jitter specification of most standards. The 30% UI is the must. Second, our EQ with CTOE and DFE ability shows the residual ISI related DJ is 12% UI. Third, the intrinsic RJ of the data path from the CTOE to the sampler after the high-pass filter at CDR bandwidth corner frequency shows 1% UI for BER equals YE minus 12. Fourth, other digits from the reflection, crosstalk, and supply noise shows only 3% UI owing to a good design exercise. Fifth, the simplest setup hold time may require a total of 10% UI for the needed arrival time before and after the data transition. After figuring out the data path, sixth, we need to check the intrinsic RJ of the sampling clock from the CDR after high-pass filter CDR bandwidth corner frequency, and that shows 3% UI for the BER equals E minus 12. Seventh, the intrinsic DJ of the sampling clock from the CDR's hunting jitter of tracking behavior or supply noise introduced the jitter would be 12% UI in total. Lastly, most people apply multi-phase half rate clock or quarter rate clocking, and the residual phase error could be 2% UI after phase calibration to reduce eye width further. Finally, the total eye closure in eye width is 73% UI, and the link budget of the eye width is 27% UI to make the link meet BER equals 1 minus 12 with margin. If we can evaluate the link budget further, you will realize the link can even meet BER equals 1 minus 15. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting.